So today we're going to talk about related rates. So let's look at this first problem to understand exactly what this means by related rates. What rates are related? So Gina is throwing a surprise party for her best friend and wants to decorate with helium balloons. As she watches the store clerk fill the balloons, she starts to wonder, how fast is the balloon growing? So helium is being pumped into a spherical balloon. What equation relates the radius of the balloon to the quantity of the air in the balloon? Pause the video and go ahead and write down what you think that equation will be. So the volume of a sphere is 4/3 pi r cubed. So a sphere is just a big ball. So the two rates that are related is the radius and the volume, and they're both going to change differently with respect to time. So remember, we're solving for r, so for the first box we're going to let our v equal 2, and now remember we need to solve this for r. So if we multiply by the reciprocal, we're going to get 3/2 equals pi r cubed. Then we're going to divide by pi. We're going to get a decimal, and then don't forget we're going to take the cubed root of that to find what our r is. Please go ahead and fill in the rest of that table. So now that we've got the table filled in, let's look at these questions. At what rate is the volume changing? Well, these are the volumes, so each second, at what rate is the volume changing? It's changing at a rate of 2 cubic feet per second. So the way we would write that is the change in the volume with respect to time, or dv dt, is 2 cubic feet per second. Question 4 is the radius changing at a constant rate. How do you know? So again, pause the video and take a look at your radius and see if it's changing at a constant rate. So if we look at each of the time intervals, from 0 to 1 second, it changes at 0.782 feet. From 1 to 2 seconds, the radius changes 0.203 feet, and 2 to 3 seconds, it changes 0.142 feet. So no, the radius is not changing at a constant rate. So the volume of the balloon, number 5, depends on how much time has passed. So we can rewrite our volume as a function of time. So we basically have the same function, v equals 4/3 pi r cubed. It's just that we have time variable in there. So what is our independent variable? And then after you determine what the independent variable is, so pause the video to do that, then I'd also like you to write the equation for dv dt. In other words, differentiate that equation with respect to time. Don't forget to use your chain rule. So remember, the derivative of v would just be 1, so dv dt, and then your 4/3 pi is just a constant. Then the derivative of the outside would be the 3r of t squared, and the derivative of the inside is dr dt. So now part C, at the instant when the radius is 1.5 feet, how fast is the radius changing? And so the first thing I'd like you to do is simplify this equation. So first of all, if you notice, those 3's are going to cancel. So we have dv dt equals 4 pi times r of t squared dr dt. And now what exactly do we know? So don't forget that way back up on number 3 up above, we know that our dv dt is 2. And we know that our radius we're given because we want to know dr dt when our radius is 1.5 feet. So now we can also plug in 1.5 for our r of t. And then that leaves us nothing but constants. We can solve for dr dt. So again, go ahead and do that, please, after you pause the video. So hopefully you were able to solve that for dr dt. There's my work. And you can see that at the instant that the radius is 1.5 feet, the radius is still growing at 0.071 feet per second. So is the radius growing faster when the radius is small or when the radius is large? And how do you know? So again, I'd like you to pause the video and look at your equation from the previous page, maybe manipulate it a little bit, and see if you can make a conjecture on this. Some of you are probably able to come to this conclusion without solving it for dr dt. But to make sure that you are all able to see this, I wanted to solve for dr dt. And you can see from this fraction, when the radius is smaller, dr dt is larger. And as the radius gets larger, then dr dt is getting smaller. So to answer the question, the radius is growing faster when the radius is small. Now let's take a look at those important ideas. So the first thing you should do is draw a picture. This helps you, if nothing else, just relate what kind of variables you're dealing with. Then write an equation that relates all the variables in the problem. This is usually, for these problems, going to be a volume, an area, or a Pythagorean theorem kind of problem. Now, after you've written the equation, the only values that you want to plug in at this point are values that don't change at all ever through the problem. Third step, take the derivative of both sides. Don't forget the chain rule. You are generally going to be taking the derivative with respect to time, so every single variable is going to have the chain rule involved. And then finally, plug in the known values and solve for the quantity you need. So at this point, you're going to solve in if you're given a rate of change, or if you're told to find a rate of change when a radius or a height is a certain value. And then finally, based on the context of the problem, determine if the rates should be a positive or negative value. All right, so let's go ahead and look at this first problem. A cylinder is filled with water, has a radius of 4 feet and a height of 11 feet. Water is being drained from the container such that the height is decreasing at 0.1 feet per second. How fast is the volume of the water changing? So what are we trying to find? How fast is the volume of the water changing? This is going to be your dV dt, which is what you're going to find. I'd like you to pause the video, and then I'd like you to draw a picture of this and do at least part A. Okay, so I've drawn my picture, a cylinder, and the equation that relates all the variables. So keep in mind, we're talking about a volume, and we're talking about a cylinder. So sometimes students get freaked out because they are afraid they have to memorize these formulas. A cylinder is simply a circle, pi r squared is the area of the circle, times the height. So the volume of a cylinder is not a hard function to remember. I also made note that the height is decreasing at 0.1 feet per second. So later down the road, I'm going to need to know that my dH dt is negative 0.1 feet per second. Which variables are remaining constant? What doesn't ever change? We're told it has a radius of 4 feet and a height of 11 feet. Is either one of those changing? Well, the height is decreasing, so the height isn't staying the same, but the radius of my cylinder as the height changes isn't going to change, right? So my radius is a constant. I can plug 4 in for my r. So my equation now is V equals 16 pi h. So I think you can go ahead and do part C and D, differentiate that equation for dV dt, don't forget the chain rule, and then plug in the known values and solve for the quantity we're after when we're all done. Pause the video and do part C and D, please. Okay, so differentiating that, we get dV dt equals 16 pi dH dt. Plugging in our known values, we're going to get negative 1.6 pi cubic feet per second, which has a little bit more meaning if we write that as a decimal, which is negative 5.03 cubic feet per second. Second and final problem. Ashanti and Cale met at Starbucks and are now returning home. Ashanti heads north at a rate of 80 yards per minute, and Cale heads east at a rate of 110 yards per minute. After 15 minutes, at what rate is the distance between them changing? Go ahead and draw a picture to represent this problem, and while you're at it, go ahead and write down the information that you know. And then I think you can also get to part B, so you can write an equation that relates Ashanti's distance and Cale's distance from Starbucks and each other. So I'm hoping you recognize that this was a triangle problem, so we simply drew a triangle, and we know that Ashanti heads north at a rate of 80 yards per minute, so my dA dt, the rate at which Ashanti is moving, is 80 yards per minute. And dC dt, the rate at which Cale is moving with respect to time, is 110 yards per minute. For part B, I prefer to use meaningful variables, so I changed my x to the a for Ashanti and my y to c for Cale. And my equation would simply be the Pythagorean theorem, a squared plus c squared equals z squared. Now, part C, again, I think you guys can finish up this part C and D, so I'd like you to pause the video and do that. Take the derivative of both sides. Again, remember that you're doing this with respect to time, so we have the chain rule. And then after you do that, plug in your known values and solve the quantity you are looking for. So you perhaps have run into a slight problem. We've differentiated, and now if we go to plug everything in, I have something. Do I have something to plug in for A? What is the distance of A? So after 15 minutes, he's moving at a rate of 80 yards per minute. So after 15 minutes, he will have gone 1,200 yards. And Calc, moving at a rate of 110 yards per minute, again after 15 minutes, he will have gone 1,650 feet per yard. So then we need to find, at that exact moment, what is this distance between them using the Pythagorean theorem. So go ahead and pause the video and use the Pythagorean theorem to find your z. So now we've used the Pythagorean theorem, we've found z, but again, it's asking for at what rate is the distance between them changing. So it wants to know the rate that z is changing. So we need to plug everything in, and now we should have all the information we need to plug everything in and solve for dz dt. So for the final time in this video, go ahead and pause the video, plug everything in, and get your solution. Hopefully you'll match what I get. So I find it easier to solve for dz dt. If you notice, my 2's cancel out, plugging everything in. We come to realize that at 15 minutes, the distance between them is changing at 136.015 yards per minute. All right, we will see you at the next meeting, and I hope you have some questions. Or maybe not, because that means you've understood it all.